Hello, everybody, and welcome to today's presentation from the Viessmann Academy here in Canada. Today's topic we're going to have a look at is application and piping for condensing boilers. I threw in, this is a 200 to 300 level training, so it's going to be focused around our Viessmann 200 and 300 level controls, standalone controls basically. We're going to try to cover here, and today I've got virtually by my side in Waterloo, Ontario, Academy instructor Mark Norris. Are you out there, Mark?
I'm here, Scott. How's it going in the West?
Doing well. So far, so good.
Good.
Just getting down. Mark always gives me a little bit of a hard time for my presentations because I tend to drone on and go a little bit over, just a little bit over an hour. So we suggested today I give you a bit of a heads up on this one. I played fair with the last presentation on Therm Protect. I was kind of in that hour. There's lots of material on this one. And Mark, it's going to be a little bit over an hour. I'm thinking probably closer to about 90 minutes to get through this completely. We'll see how it all
There's a
works
lot of
out
material
here.
to cover. Good
A
stuff
lot
to
of
stick around for.
information. Absolutely, but good information. Like I say, that the key of what the attempt here is to really link, application of condensing boilers and our Viessmann controls. How we will help you basically, squeeze out as much efficiency as possible. We give you the controls to do that with these boilers, and then kind of throw in some piping information in there as well. The different types of boilers that we have available, and how Viessmann approaches those different piping strategies as we move through here. So hopefully that's going to kind of sync through with the different slides and stuff that we've put together here. So what's up with
If
you
you have
today,
any
Mark? What are you
questions,
going to? Yep.
I was thinking about you this morning because it was raining like crazy this morning. But it
I
seems to be all right.
appreciate that, man.
I can look from my office through the hallway to the counting office, and I can see
So that
trees.
gives you what Mark thinks of me. When he sees a rain cloud, he thinks of me. It's very nice.
That's right.
Appreciate that.
Because it's just because of your location, man. Every time I'm out there, it's raining.
It's true. That's why
Even
the
when it's
coffee's
supposed
so
to be
nice here.
snowing, it's raining.
That's right.
So, anyways. We've got a question box. You guys can ask questions in as you go along. I'll try to keep up with them in real time, and anything we can't keep up with or I think Scott should handle, I'll hold to the end. But if you ask the questions in the Q&A box, not in the chat box, because the chat box doesn't record as well. With Q&A, we get the questions and the answers, and we can send those out with the presentation later. So if you want to do that, that'd be great. And I'll give it back to you, Scott, so that we're already into this now for time.
Yeah, let's get going on this. So basically, we'll start off here. I have just a little comparison of condensing versus non-condensing boilers, and we kind of label these condensing and non-condensing. But as you'll see as we move through here, we can reverse these as well. A lot of applications you'll see condensing boilers out there, and they're in an application where there actually is no condensing happening, and you could have potentially a non-condensing boiler that's labeled non-condensing actually out there condensing. So we'll have a look at that as well. But in reality, when all things are basically on the same level here, when we're looking at condensing versus non-condensing, it really has to do with temperature, a large part here. So we have a system where based on the day that we're looking at, 120 degree Fahrenheit is going to satisfy that particular building load. You'll see that the non-condensing boiler, because it's non-condensing, we have to keep those temperatures a little bit higher. We can't drop down below our magic dew point temperature. We're going to look at that in a little bit. So 160, 140 on the non-condensing boiler to basically satisfy that load on this particular day, where the condensing boiler can dial that temperature fairly accurately right into what we're actually looking for to send out to the heating system. So that lower temperature right away is going to be more efficient, just because we're not going to cycle as quickly. This boiler here probably will cycle a little bit faster because we're going to satisfy this load a little quicker. That could also cause some issues with comfort as well, right? The whole idea there is, rapid changes in temperature tend to create some comfort level issues. So if we're delivering the right amount of BTUs for the heat loss of the building, that's going to have a direct impact on the efficiency of the boiler, but also the comfort level of the building, which is what we're going to get into here as we move through. So without even looking at that, just looking at straight losses as far as the amount of energy. So we're throwing in 100% of the fuel input, the natural gas going into these boilers, both of them, same heat losses, same loads here. When we look at heat loss, or standby losses, I should say, basically you can kind of define that as we're going to burn, of the 100% of the energy that we've actually burned, that cubic foot of gas that we've burnt up, how many of the BTUs is actually going in to heat the space that's actually looking for that heat, and what percentage is actually just being dissipated through the boiler jacket, through piping losses, etc. And hot boiler rooms is one area where you see a lot of standby losses. I know I've cleaned a lot of boilers, in the summertime, and it's 90 degrees outside. You walk in the boiler room and it's, 120 degrees inside the boiler room. That's got to be some losses there. That energy is basically dissipating and just overheating a boiler room. So there's some losses that we're dealing with there. Obviously, system piping as it moves through different spaces. The hotter the piping, the more energy it gives off based on the ambient temperature around it. So you have some losses there. Draft in your venting systems. I mean, there's a lot of atmospheric boilers out there where the draft damper stopped working years ago and it's just stuck open. Of course, that is just basically, pulling that energy right out of the boiler and pulling it up through the stack with the draft. You could have post purges on your boilers as well. So after the burner fires, it's got to run the fan for a while or something like that. Those are all losses that are standby as that boiler is in operation. We're essentially cooling that boiler temperature down, and that energy is escaping through the chimney when we do any type of post purging of our burner fans. And in some areas, we have to maintain a boiler minimum threshold because it's a non-condensing boiler. So that boiler has to get up to a specific level before that pump can even start, to protect the boiler from any type of adverse reactions of having that low temperature coming back to the boiler and thermal shock and all those things that we're looking at. So a lot of this makes up those standby losses. And conservatively looking at these units, 5% non-condensing loss here, fairly reasonable, and we're up to about 3% standby on our condensing boiler. So out of that 100%, right now we're at 97% is for usable heat in the condensing application. We're at about 95% of that 100% going up currently into our heat emitter there. Let's look at the stack side of it. So combustion side of the boiler, you can obviously see the stack is much larger on the non-condensing boiler versus the condensing unit here. That's because we don't want any of this flue gas to condense. This is where the energy is, right in this steam that you see coming out of the top of the chimneys here. With a non-condensing boiler, we have to make sure that none of that flue gas hits dew point. So oftentimes what happens, we'll make sure that there's a specific temperature here that will ensure that flue gas escapes without any type of dew point being hit and having condensate run back down the venting system and effectively ruining the vents in a short period of time. So we need to protect the system here in a non-condensing application, and that might elevate the stack temperature during operation to make sure that we protect that chimney. On the condensing side, we're really trying to get that boiler condense inside of the heat exchanger. But oftentimes, as the exhaust gas comes out of the chimney here, the stack, it actually hits dew point, and that will run back down, and sometimes it goes through a drain T or something like that in your venting system. In a boiler like a Vitodens 200, for instance, that condensate actually gets back down in the heat exchanger, and you get some sensible heat exchange there as that dew point, or the temperature that condensates a little bit higher than the return temperature of the boiler, and that will actually exchange a bit of heat, so you actually get a little bit of recovery off of that. But that's the difference here. Smaller vent because we have less flue gas that we have to deal with as a result of a boiler that's in a condensing application. For every 50-degree stack temperature change, that's a change in efficiency of about 1%. So you can see the rate there, 325 versus 125. There's a difference of about 200 degrees. So our condensing boiler is right off the bat, it's about 4% more efficient combustion-wise because of a lower stack temperature than the one beside it here. When we're talking about condensing a boiler, so we're just looking at the sensible side of it there as far as the combustion test and having a look at the actual temperature of the exhaust gas going out. When we're looking at latent heat, that's the other amount of energy that's going out through that steam or that exhaust gas as it moves through the chimney. If that, in order for that steam to be created, it had to absorb 970 BTUs for every pound of water that we turn into steam during that combustion process. So it sucked up 970 BTUs to draw it out up through the chimney as steam. In a condensing boiler, we actually want to cool that steam down and pull that 970 BTUs back into our heat exchanger, our boiler, so that we can use it to heat the building. So the difference here is for every pound that we condense, we are gathering or adding 970 BTUs per pound into our heating system. A non-condensing boiler, basically for every pound of condensate that is turned into steam is going up our chimney as a 970 BTUs. And if you look at the value of a gas, cubic foot of natural gas here, hovering around 1,000 BTUs per cubic foot. Very easy to relate. For every pound of water we get out of our condensate pipe on our condensing boilers, that's about a cubic foot of gas that we're saving as a close relationship there. So the amount of energy in that plume of steam going out your chimney could add up to about 10% of the total amount of energy that's in that cubic foot of gas. So it's very important for us to get that exhaust gas to condense in the heat exchanger to extract that amount of energy. So as you do your combustion test, you really can't see that amount of energy and how it changes your efficiency. We have to actually know how much condensate we get out of it. So I pulled this out of our data manuals for some of our smaller boilers around the 100,000 BTU range. And based on the return temperature of 100 degrees Fahrenheit, about 0.8 US gallons an hour could be anticipated coming out of your condensate pipe. Now that's about 6.64 pounds of water condensate at 970 BTUs per pound. That's 6,441 BTUs we add back into this amount of our input or fuel input. So we actually add that back in, that extra 6.5%. So we have a total amount of 10% of the latent heat that's in that exhaust. We extracted another 6.5% of that. So about 3.5% got away from us and escaped through the chimney. So there's your condensing boiler. There's a Vitodense 200 heat exchanger as it condenses. You see the droplets here. As we start aggregating and getting this collected in our condensate pipe, and it flows out into your neutralization tanks and out for every pound. That's adding back into your system here. So if we add up the latent heat and the stack losses here, we have a 16.5% loss. And then the latent heat side, we add basically the 3.5% that we've lost up the chimney here, plus the stack losses. So we're at 6% versus a 16.5% loss on the condensing boiler on the combustion side. So a lot more of the energy actually getting into heating the building. Now you can have a non-condensing boiler condense, as I mentioned. It's possible. We could drop that temperature down. A lot of boiler manufacturers with non-condensing boilers are really going to try to stop you from doing that by adding controls in there that'll limit that return temperature. But it is possible, and that's what a non-condensing boiler is going to look like after a short period of time if we allow it to condense. So the reality is the magic really, there are other factors involved on the combustion process, your CO2s, et cetera, are important here. When we look at that, but all things being equal with modern boilers and modern burners that are dialed into some pretty high efficiencies as far as their fuel air ratios, it really comes down to that return temperature. So we can make any boiler condense if we get that return temperature down low enough, but it is the difference between protecting that system or not protecting the system. So a non-condensing boiler, we want to make sure that we don't dip down below the dew point, or otherwise you're going to look like you got a boiler that was installed in Davy Jones' locker or something like that. So a lot of rust and et cetera. So lots of articles were printed years ago talking about what's raining inside of my boiler, that sort of thing, and that's what happens when a boiler condenses. And the materials have to be of an acceptable type that we're not going to see that corrosion occur. So when we put the two together, this is why you look at the side of a boiler and you say, well, the AFU in this boiler is 86.5, and this boiler is a condensing boiler. It's 95, AFUE. But I put these boilers in, and the difference in the actual total efficiency was over, a 30% energy savings year to year, or 40%. We see some of these crazy, amounts of differences between condensing and non-condensing boilers and the fuel savings and cost savings over a period of time. time. And that really comes down to, when we start looking at the actual real world, AFUE really doesn't come into it when you're dealing with different types of temperatures. So those return temperatures, supply temperatures, and of course, temperatures going up the stack really come down to what that actual amount of efficiency is going to be. And that's kind of what we're dealing with here. So how do we, look at maintaining or achieving a high efficiency heating system? We see there, a lot of that's based on temperatures, et cetera. The biggest goal that we really want to achieve here for the occupants of the building is to make sure they're comfortable. So it doesn't matter if your system is 100% efficient. You turn the boiler off, you're not going to burn any gas, but is that space going to be livable when the temperature outside gets to design? So it's all about comfort for the occupants. And then we want to use as much of that fuel that we burn towards that first goal of A, to make sure that the level of comfort in the building is maintained, and we're not basically throwing that energy out the chimney or in the boiler room where we don't really need the heat to be located. And obviously we want to make sure that the components are protected in the system. So we don't want to have too high or too low of a temperature in some cases, to make sure all the components live out their life cycle without a lot of service, and replacements and repair costs. Those all basically start to reduce the efficiency, because now you're going to have some of those costs to keep and maintain those components. The challenges, the things that get in our way when we're doing this, is basically we're dealing with a moving goalpost here. So one day your building might heat wonderfully. The next day it might be way too much heat or way too little heat there. So there's a lot of changing conditions there, both inside and outside, that we have to deal with. And when we get into efficient heating systems, a lot of times, it happens in everybody's life where you go and you buy a boiler, you buy some controls, off the shelf, you put all this stuff together. There's priorities, there's multiple temperatures, there's things that you have to deal with there. And, you kind of sit there, scratch your head on how you're going to make all this stuff work. It gets to be quite complex when we start dealing with, high efficiency heating systems and all of the different things we have to basically look at to ensure that we achieve these three goals that we're setting for ourselves here. So we have to understand, basically look at what we know about heat losses of a building. Let's start with the basic stuff and kind of work towards that bigger goal of that efficiency heating system. And what we know is the moving goalpost a lot of times is the fact that the outdoor air temperature is changing. So as we get into the heating season here, we start dipping into those temperatures that get down to where we need to turn the thermostat on. That is, all based on what happens outdoors, the outdoor air conditions. And you get these shoulder seasons where one day it could be, +5, the next day it could be +15. We're going to have some real issues trying to control the temperature inside the climate inside the building with these changing conditions, because we want to keep the indoor temperature as relatively constant as possible. Keep the people at a comfort level that they're used to. They set a thermostat, and generally speaking, they tend to leave that thermostat at that particular position. And as long as they're comfortable, they're not going to make a change in that thermostat set point. It's when they start becoming uncomfortable, they start to change those characteristics. And that could be because we're not doing any adjustment to boiler temperature when this temperature outside is changing. So basically our biggest challenge here is to try to match the load of the building as the temperature outside is really changing from sometimes minute to minute, hour to hour, day to day. And let's have a look at what we're talking about. So we're dealing with the time that we're trying to heat a building. So we need to talk about the heating season at different locales, different areas. I've got a couple of cities here in Canada for us to look at here. And the total amount of heating hours in Vancouver, so my little corner of the world here, if you added up all these hours, we're at about 6,536 hours of time that we are down below our indoor temperature. So when we're talking about heat loss calculations and all that kind of stuff, we need to know where we want to keep the temperature inside. So we see, once we get to 68 degrees Fahrenheit, about 20 degrees C, in this area where we don't want to heat anymore. We don't need to heat. That's the temperature we're trying to maintain in the building. So after this point, we don't have any more hours of heating. So This is really talking about the total amount of hours we're down below that 68 degree Fahrenheit when we need to heat the building. When we're trying to design a heating system, we need to know also how cold it's going to be in that particular area where that building is going to be located. And here in Vancouver, our design temperature is about -9 C, 16 Fahrenheit. So if we do the math here, the boiler, when we select a heating system here, a boiler, it has to essentially ensure that it can deal with a temperature adjustment here of about 52 degree Fahrenheit outdoors to indoors. So it might be as wide a temperature differential as that when we are trying to maintain a comfortable living space with that wide of a delta T. So you can see there's quite a bit of a challenge there that we're looking at. But if you also look at this, you can see that we spend an awful lot of time here in Vancouver with temperatures much higher than that design temperature. Right? So again, we're modulating here as the load is going to modulate from 100%, everything basically calling in your building to a fraction of those as the temperature outside warms up. And of course, the boiler has to do a similar capability. It has to be able to do those modulations as well. The other side of it here is the supply temperature. So based on the outdoor air temperature here and what's going on, you see a number of temperatures here, and we have to determine what temperature we need to send out to our building to maintain this temperature inside when the temperature outside is somewhere down in this area of the as far as outdoor temperature, or even up to the design temperature here. So that is kind of where we get into the heat loss calculation. We go to another city here just to give you a bigger differential. It's actually known as Winnipeg up here, or Winnipeg, Manitoba. And you'll see that they have a much wider temperature. We're trying to maintain 20 degrees here, but we're at -29 degrees outside at 68 Fahrenheit inside. There's a 97 degree Fahrenheit delta T here. One thing that is to benefit, if we actually look at the amount of time Winnipeg spends below 20 degrees or 68 Fahrenheit, it actually has 100 less heating hours than Vancouver does. So even though we have a warmer design temperature, we actually stay below 68 Fahrenheit here for another 100 hours of the heating season. So when they're putting the SPF on in Winnipeg, we're still got our thermostats on heat here. So a bit of a difference. But again, it's about that design. What are we actually going to have to send out to the building? And there it is on our vertical here to maintain the temperature that we're looking for in the building here as the temperature outside is changing from, like I say, hour to hour as we move through. And I'm going to add in another little line here that we need to understand for condensing operation is when we operate our heating system that we dip down below this yellow line, and you've probably seen this in lots of presentations. This is the key to condensing boiler operation. If we get down below the yellow line, we're going to have condensate come out of the boiler. If we don't dip it down below this yellow line here, then we're going to have more flue gas escaping, and of course all that latent heat in that flue gas is going to escape with it, and we're not going to basically pull that back into our heating system. So there's an important area here when we're talking about efficiency, is designing so that we're down below our dew point temperature as often as possible. So if we look at boilers, and of course we've all these condensing boilers that are out here, you'll notice that they have max temperature or max inputs as far as BTUs, as well as min BTU inputs for low fire. And we also use a sensor in all of our 200 and 300 level of boilers. So there's a boiler sensor in our B2HBs, CU3A boilers as well. We've got a boiler sensor in here, but again, modulation. So you can see that as the temperature outside changes and we need more BTUs, we're going to design this heating system for maximum output. So we select the boiler that's going to give us at our 100% requirement for our outdoor temperature, how many BTUs we need. We size that boiler accordingly, but with modulation, it can match the load of the building much easier because it can start to ramp down as that boiler doesn't, or as that heating system doesn't need as much heat because there's not as many zones on. And in a Viessmann boiler, that number 3 sensor is fairly critical. When the boiler fires up here, we got a call for heat. How does that boiler know what that load is? And when a Viessmann boiler fires up here, it fires ignition point, and then it drops back to its base load or low fire position, and it starts to monitor that number 3 sensor. And if the temperature is picking up on low fire, then that burner is going to maintain a low fire position because it understands at that point that there really isn't a lot of load here. So it was only one zone versus all these zones open. And of course, that return temperature is essentially picking up. So it's gaining on the system in a low fire. It's not going to want to go to a higher position. If the temperature starts to drop off from the set points, we start to lose ground on the heating system. It understands there's more zones open, and that burner is actually going to start to increase its modulation. So the whole idea here is it's an anti-cycle logic in our burner controls to maintain low fire as long as possible. And as long as we're picking up temperature, there's no need for that burner to fire up to a higher position, because that's going to create basically a set point being met quicker, and of course the burner is going to stop or cycle off, and that's going to basically increase the cycle times of the burner, which is where we start losing efficiency. So what's the importance of high fire or low fire position of our burner and condensing boilers? If we think about the heat exchanger that was designed for this unit, so if we had a 199,000 BTU boiler here in a CU3A, but we were firing at the lowest input, we have basically a 5-to-1 turn down on CU3A. So it would be about 20% of that burner or that boiler's maximum input. So that heat exchanger size for that 199,000 BTUs, we were firing 20% of that. That heat exchanger is going to be really capable of absorbing all of that energy because there's so much heat exchange surface area for it to get in contact with, which reduces the stack temperature, right? Remember that 50 degrees, we drop 50 degrees, and that's an increase in combustion efficiency by 1%. And to the point where we actually might grab some latent heat, where we start to get that flue gas temperature dropping down below our dew point, and now we start to condense at a low fire position. So there's a large advantage to the burner staying at low fire as long as possible, as long as they're maintaining the comfort level in the building. And that's what the Viessmann control logic will do for you, is to essentially try to match that load as the temperature outside changes. The burner can modulate and basically try to match the BTU input by monitoring that number 3 sensor to see if it's gaining or if it's losing ground on that heating system. The outdoor temperature, as we mentioned. So now if we add this to our modulating boiler control, we feed back information now to the burner. So if you ever bought a VitoDense 200 or a Vito Crossel 300 CU3A, you open up the boiler package, and every one of these is going to come out with a outdoor sensor that you can mount on the wall and run back to a particular point on the control. And now you're feeding the boiler what the outdoor temperature is, and we can set a heating curve. We're going to look at that in a little bit. And now that burner or boiler will now start to track the outdoor temperature and give you a specific supply temperature based on that outdoor temperature. So now the set point isn't the same every day. It's going to float based on what we're dealing with on the outdoor temperature. And that's going to basically help us achieve our efficient heating system goals that we're looking for. Comfort and, of course, energy savings and all those good things. If we match those two together, people are happy and they're also saving money. Then you see the nice smiles they have on their faces there. So they're basically all sitting there planning their trip to Disneyland right now. So that's where you can do with your, that extra money that you find in those seat cushions when you start to basically try to dial in the efficiency of your heating system by using like an outdoor reset control, for instance. So our control built onto our Viessmann system. Let's throw that heating curve on that basically the time spent in different outdoor temperatures here in Vancouver, and the little dew point line sitting there. And again, we still are dealing with what temperature are we going to have to supply out to maintain our building at the 20 degrees or 68 Fahrenheit when it's that -9 or 16 degree Fahrenheit. That is going to be all based on what type of heat emitters or what type of heating system we're going to install in that building. Is it going to be a high mass type of inflow radiant system? Is it going to be, cast iron radiators or panel rads? Is it a fan coil you're installing, baseboard? All of these different emitters are going to require different supply temperatures based on our outdoor design temperature here. So if you start mixing and matching these, you start getting into multiple temperature systems. So now instead of one heating curve, you might have to do multiples heating curves, because now you might have one that needs a specific temperature at one point in time, where that other, high mass radiant system is going to require something quite a bit lower. So let's have a look at some of the challenges we have in designing for these lower mass systems, really, like your baseboard and fan coil systems, where you're typically selecting a fairly high heating curve, fairly dramatic change in temperature as the outdoor temperature changes, both plus and minus. What can we do to kind of basically get these systems? These are the biggest challenge as far as condensing operation when we get into it, really, are these low mass type of heat emitters. So for example, we've got a 4-zone system, 100,000, or what do we got, 50,000 BTU heat loss in this building. And I've basically thrown the graph up here. We have 12.5 thousand BTUs per zone with a 20-degree temperature drop. If you had 25 feet of baseboard in each one of these zones, you did the math on that. We see down here, somebody much smarter than me already came up with the engineering information on this piece of baseboard and what it's going to be able to do at different temperatures that we supply it. When we look at this, basically what we'll do is we'll add these two numbers together, divide by 2. The average temperature sits right in the middle here, about 170. When we're looking at designing the system, when we multiply the 25 feet of baseboard that we have here by about 510 BTUs per linear foot, we end up somewhere around that 12,500 BTUs. I think it's like 12,750 or something like that. So a little bit over. But when we look at this, that would tell us that if we have 25 feet of baseboard and we do the math here, we need to make sure that we supply 180 to that system. So now our heating curve we're going to select is based on 16-degree Fahrenheit outdoor temperature, 180-degree Fahrenheit supply temperature. We're going to be picking this 1.8 heating curve to make sure we have the right temperature when it's that cold outside. But if we look at our little return graph here, at this point, that little return water temperature line here drops down below our dew point. So at about +3 or about 37 Fahrenheit, we're going to start to condense, even with a high temperature system like this, if we have it an outdoor reset. What if we decided instead add 30%, 33% more baseboard? So instead of 25, we put in another 8 feet. So we have 33 feet of baseboard in those zones now. So we added more baseboard. We can drop the temperature down now because we have more lineal feet of baseboard to work with. Again, still a 20-degree delta T, 160 down to 140. So our average temperature is 380 multiplied by 33 gives you somewhere around that 12,500 per zone. But now have a look at where we're hitting dew point here. So about another 15% of the heating season, when we add that much more baseboard and drop that supply temperature down, we're now condensing at about 28 Fahrenheit, about -2 outside instead of +3. So 5-degree difference here in Celsius and our dew point when we start condensing, which equated to about, like I said, about 15% of your heating season additional time spent in the condensing mode. So that extra bit of baseboard is going to pay for itself in a very short period of time here, because now we're dealing with a condensing temperature much quicker, but also a drop in our supply temperature. I'm going to get to this in a minute. So we went from 180 down to 160. There is some energy savings just in that sensible change as well. We'll have a peek at that in a moment. Same thing here with a fan coil. We have a couple of selections here. These are Viessmann fan coils, AH2A 213s up to 385s. Different supply temperatures here. So again, 70,000 BTU heat loss with a 16-degree outdoor temperature design at a 68-degree indoor temperature we're looking for. I could select the smaller unit here and supply at 180-degree Fahrenheit, and it's going to give me about 72,000 BTUs. So that gives me about 75% of my heating season. I'm in the condensing mode, somewhere around there. If I went to the next size up, I could supply now 150 to 130 and get basically the same amount of BTUs in here that we're looking for. But now I'm condensing 100% of the heating season because now I'm down below the dew point temperature here, right at the design. So the difference here basically is about 25% of your heating season, you're condensing versus non-condensing. That's going to pay for itself in a fair quick order, specifically because really the difference between these two as far as costs is probably just a couple $100, I think. So really not that much of a difference. So it really starts to kind of, you're talking about efficiency. It's all about, there might be a little bit more capital cost at the front end, which there often is, but it's all about how quickly we can start paying things back. And that's where we start getting into those design criteria. So let's have a little peek. I'm talking a million miles an hour here because I had lots of coffee today. Again, trying to get through this presentation, so my apologies. But this little graph here, there's actually two of them. And these are in a lot of our manuals, and they cause a little bit of confusion. I'm going to try to kind of clarify this one up a little bit here. So if you look at these two graphs, they are related. They're trying to give you some information here. You're dealing with basically in this system here at -4 Fahrenheit, about -20 degrees C is our design temperature. So that's when we have 100% of our heating load is going to be required. And there we see on this graph, we see 100% right here. So this is where the relationship is, a starting point at 100%. And then 30% load we see here, that's going to be the shoulder seasons of the heating curve in this area. And then we're looking at comparing three different types of systems. So a high mass radiant system at about a 0.5 heating curve. That's the little red line here. We have a 1.4 heating curve, which is the standard default heating slope on a Viessmann control made for coming out of the box. At 1.4, like a staple up type of radiant system, and then a low mass, copper fin tube baseboard system at 1.8. We see the light blue line here. And the whole idea here is to have a look at comparisons of design versus the shoulder seasons, the change in efficiency of these systems as we use a heating curve. So we see the difference between a high mass heating system from design temperature to shoulder seasons is about 3%. We go from about 95% to about 98%. Our temperature changes here are minimal as far as the supply and return. And that's because it's a high mass system. There really is not a lot of adjustment as the temperature outside changes. So we basically change about 3%. We get over 10% change in efficiency from design to shoulder seasons with the staple up system when we put on a heating curve. So we go from about, just under 86% efficiency here up to somewhere above 97% on a heating curve. And then copper fin baseboard, we were right around 10% change in efficiency from design to basically the shoulder seasons. And the whole idea here is that if you look at it, if we add outdoor reset controls to these low mass, high temperature systems, to a greater degree, they're going to impact our efficiency of our systems. So really the low hanging fruit is kind of your high mass radiant systems. They're pretty much condensing regardless of what we do. And we're going to have some subtle adjustments there. Not to say there's no value in that, but to a greater degree, heating curves are going to impact those high temperature systems and get those into operation. So when we do get boilers into condensing, the importance of that, how quick we get into condensing is going to make a difference as far as your payback over a long period of time. So during a shoulder season, we're down that 30% load type of time of year, your boilers are going to be condensing, giving you about 3 to 4 gallons of water per day of condensate, which equates to about 32 cubic feet of gas, or about 32,000 BTUs of energy recovered from the flue gas. So that doesn't seem like a lot, but do that for 20 years, 15, 20 years. That is a large amount of energy savings, basically going back into the pockets of your homeowners. During those design days, when we're at basically maximum requirement, you can get up as high as 20 plus gallons of condensate coming out of those boilers. So now you're up into 178,000, 178 cubic feet of gas savings per day at those design conditions. So there is a lot of value the quicker we get those systems to get into condensing. But what if we don't have a lot of that ability? So we're kind of dealing with an existing system. You got baseboard in there, or you got some staple up irradiant system. You can't add any more baseboard. You got a fan coil that's basically sitting there, and there's really not much you can do as far as adding more, so we can drop the temperature down, so we can change the slope of the system. But remember, the only thing the curve here does is set your supply temperature. It doesn't adjust your return temperature. That is based on a engineered design. So delta T is really a design criteria. It's not really set so much up on the heating curve here as we design it based on the type of emitters that we're going to apply to the system or what's existing. And that delta T is part of your heat transfer equation. So this little scary equation we see coming up on the screen here. And basically all that means is if we want a certain amount of BTUs going out, it's going to be a function of the gallon per minute of flow rate in that system multiplied by the delta T times this constant of 500. So there's the delta T, and these are variables. We can change a variable, and when we change that variable, it's going to have basically a change or adjustment in other variables in the equation as well. So let's have a peek at this equation and what we're dealing with. The 500 constant, been lots of seminars lately or presentations online lately that we've been doing with outdoor reset and this energy equation. And we understand that this is a constant for heat transfer using water. If we use something else other than water like glycols, etc., there will be a reduction in this number of 500. So 50% glycol, you might use 450, for instance. I've heard rumors. There also, about 30% glycol is about 480, I think it is. So basically, if you start using glycol, it's not going to transfer as much heat. The specific heat capacity of the fluid is going to be a little bit lower. Thus, that's going to impact the amount of heat transfer that we can get out of the system. So we're going to use 500 here because we're using water. And we see here that we've got a 9 gallon a minute flow rate. We've got 180, 160 degree return. So there's our delta T is 20 degrees. So we got all the variables in here that we need. We start doing the math on that. We come up with 90,000 BTUs is essentially what's being transferred here between the boiler and, of course, the heat emitter that's in the system. Now, what happens if we design for a 50 degree delta T instead of a 20 degree delta T? What's the difference here? Let's throw it in. We need to know now the impact's going to be on that flow rate, the gallon per minute flow rate. We still need 90,000 BTUs, but we now have changed the delta T from 20 to 50. So we have 90,000. We're going to divide that now by the 50 times the 500. And our new flow rate to get 90,000 BTUs at a 50 degree delta T is going to be 3.6 gallons per minute. So we've slowed that flow rate down of that pump to get basically that higher delta T, get that basically that return water coming back in a condensing application here. So is that possible? Sorry about that. Is that possible? It really depends on, and the challenge here obviously with these high delta Ts is when that water hits that final bit of radiation, is there enough energy capacity, carrying capacity of the water going through there to transfer enough energy to basically to heat that space? So it would be different if it was a zone basically that was feeding a bunch of bedrooms or something where you're going in and out of one bedroom to the next bedroom to the next bedroom with one thermostat. That could be a challenge with high delta T. If we had a big open space where basically everything is being fed by one large piece of radiation that went from wall to wall, that could be basically a much more agreeable area for higher delta T capability. So it's something to kind of investigate there. Again, playing with that return temperature, you can get your boiler into condensing operation up a lot quicker. Low mass fan coils, a really good application for a higher delta T operation, where basically we can send out that temperature and basically slow that flow rate down, still get the same amount of BTUs. A lot of your fan coil manufacturers, Viessmann has a couple of these different air handlers and fan coils. We give you the information there, different correction factors based on lower temperatures or sometimes higher delta T's to help you figure out based on that, if I supply this fan coil with this type of flow rate versus what's published, this would be the difference in the BTU output that we can anticipate there. So lots of material there for us to really start dialing in these particular low mass type of applications where sometimes it's a challenge to get those boilers into condensing operation. If we use what we got, we might be able to get those into condensing. But even if we don't get into a condensing mode, there is a 3-to-1 rule. And this is what I was talking about earlier, talking about just dropping that supply temperature. We talked about that 180 Fahrenheit baseboard system. We dropped it to basically down to 150. There's a 30-degree difference in that supply temperature. And that's going to have a direct impact on things like your stack temperature is going to be lower now in that burner fires. The piping losses are now lower because we have a lower basically temperature on the piping as it moves through. So your standby losses are to a greater degree are going to be reduced. All those things go towards this, what we call the 3-to-1 rule. So for every 3 degree Fahrenheit, we drop the supply temperature going out to our system. It basically decreases the fuel consumption by 1%. So if we drop that system, basically, from that 180 down to 150 that we talked about earlier in that example, that's about 10% fuel savings just by that sensible reduction. And then we start adding in the latent heat. That's when you start seeing these large, changes in the, the paybacks or the reduction in energy usage when you go from a non-condensing to condensing application. So that 3-to-1 rule applies to both condensing and non-condensing when we talk about sensible temperature drop, not the latent heat that we're dealing with. Okay. So hopefully that gives you a little bit, information on a lot of that stuff. A lot of stuff is just review, but let's have a look at the how Viessmann kind of applies this stuff in our controls. So that's kind of what you get when you buy a Vitodens 200 or a Vitacross 300. You're getting an outdoor reset control, a system control, not just a boiler control. Everything is built around the boiler and the burner as far as the logic, and basically the idea is that when we attach a system to that, we want to control that boiler to optimize its efficiency, right? So we don't kind of have we want to make sure everybody's comfortable, but don't worry about the boilers, let it operate and do what it's got to do. We want to basically interlock everything here, comfort as well as efficiency. So how we do it, there's a couple different ways our controls are set up. Heating circuits, always been kind of a mystery wrapped in enigma for some people here, but heating circuits basically are just based on your temperature requirements. So it doesn't matter how many zones you have in a building. You could have 50 zones in a building. If they're all requiring one temperature, we would call that heating circuit 1, just one supply temperature. If you have basically another heating circuit, basically another temperature. So now you have some baseboard and you threw in a staple up system in another area of the building. Those are going to require 2 different temperatures. Again, doesn't matter how many zones per circuit we're dealing with. We're just separating this particular system needs that temperature, while this system in operation is going to need a different temperature, and the mixing valve is added to basically reduce that temperature going out. So that we get the right temperature going into that heating circuit. And finally, we have HC3. So you'll see the boilers out of the box here are capable of 1 temperature. If we start adding mixing valve systems or kits here, we can get up to 3 different temperatures on 1 boiler. And those little kits look something like this. So you've got the mixing valve module here. You've got the actuator. The actuator sits on the mixing valve, and it's a 120 volt floating. The control here links back to the boiler for communication. So now you're integrating the boiler and the actual mixing circuit. The boiler knows what's going on there and it's going to react accordingly. This also gives you your 120 volt floating signal that's going to basically open and close this mixing valve, a pump output, as well as the sensor inputs and communication for the control devices, etc. So everything basically built into this, and we add a sensor in here strapped on the pipe. And now we have the capability with a Viessmann control here of adding mixing valves and now having 3 very distinct heating curves for the 3 different temperature requirements in our building. Again, regardless of the amount of zones we're dealing with, we have this capability. And the difference between this and just putting thermostatic mixing valves in here, these valves are going to save you, upwards of 5% per year in comparison to operating with just thermostatic mixing valves here. Thermostatic mixing valves are just going to give you a ceiling temperature. So no higher than this is going to go out to these zones. But during normal operation, as long as the temperature going out here is lower than that, then you're getting whatever this high temperature circuit's getting is going right out to these zones as well. So that's all a thermostatic mixing valve is going to do. It just protects the top end of that system as far as supply temperature, whereas a reset mixing valve is giving you full reset logic during the whole heating season. And again, it's all about payback. So we're at 5+% payback here on your systems in a short period of time. These valves will start to pay for themselves, and now the people are starting to save energy and again save dollars throughout the heating season. So as far as some different control logic, talking about coding, et cetera, that we have on our boilers, when we use mixing valves with our units, there is a differential setting that is encoding that the burner by default will, or basically the boiler will maintain an 8-degree differential over the mixing valve supply temperature requirements. So as far as the mixing valve goes, it's going to dial in pretty much precisely what you're looking for here. So if they have good authority on the valve here, you sized it appropriately, then this valve is basically going to maintain the temperature spot on what you're looking for, but sometimes within a degree or two kind of operation. And it's because of this differential, it's capable of doing that. If we have this, basically we dial in no differential here where the boiler is following exactly what the mixing valve is looking for, then the arm of the mixing valve is always extended out to its maximum limit. When we give it a differential, that valve now basically goes to about the 50% position. So now if you go into a typical Viessmann control system, that mixing valve during operation is usually sitting around that 50% position. So what happens when there's changes outside or load changes here, this valve can very quickly just adjust to another position and basically reset that temperature very quickly. If it's extended way over to one side, it basically has to hunt a little bit more to do that. So basically the differential here, we usually recommend between about 6 and 8 degrees C, or 6 to 8 Kelvin. Kelvin and degrees are basically essentially the same incremental values. But we use Kelvin in our coding. So the whole idea here is basically give this valve the control logic it needs to give that circuit optimum comfort as well as efficiency. So we've got a bit of a differential change here between the boiler side and the mixing valve side to give that mixing valve a bit more capability of controlling its circuit. We also have with mixing valves, Viessmann mixing valves connected to our system, what we call in this address in our coding level 2 of our heating circuit logic, A2 is your priority address. So it's usually set to 2 by default, which means when the domestic hot water heater here is calling for domestic, we're going to turn all these pumps off. We're going to close the mixing valves are attached until this tank is satisfied. Then we're going to allow these systems to operate again. With mixing valves, you have the ability of basically changing that to what we call reduced priority. And that allows essentially the boiler control here will now look at without any type of sacrifice of recovery of the domestic hot water tank. If the control sees that the tank is getting up to temperature without any issues and it has extra capacity, the temperature outside's warm, or the burner is sitting at a low fire position, it will actually allow these valves to crack open and the pumps to come on to now supply the mixing circuits here with a temperature, maybe not 100% of what they're looking for, but sometimes it would be all based on conditions. But now it allows us essentially to maintain heating the building at possibly a reduced rate while we're heating the domestic hot water. So I think of some different systems we used them very successfully. Areas where there might not have been an upsizing of the boiler for domestic hot water loading, et cetera. This will allow us essentially to, when we're in the shoulder season, to keep this heating system operating even with domestic hot water. Or if you have a lot of domestic hot water recirc happening in your system, that basically cycles the tank more often. This will also allow us to maintain heat in the building so that, again, the comfort level is not sacrificed because we're cycling the tank on and off here for recirc operations. So some real benefits here to using the Viessmann mixing valves for not just comfort, energy savings, but combined with the boiler control here to give us basically more control in an automatic type of configuration, because now the boiler is really in kind of control of what's going on with those mixing valves and how they're going to work. The other challenge with heating circuits is out of the box, those pumps that are connected to your system, P 5, 4, and 3 here. When we're running down below our room temperature outside, the pumps are always on. And that could be a problem if those are, straight fixed speed pumps, and we don't want to deadhead those circulators. This actually was a really good conversation that came up in Mark's presentation a couple weeks ago. Heads up, basically hats off to Mark. That was an excellent presentation talking about, when we might want to start and stop these pumps based on temperatures, et cetera. And if that's a desire here, these are variables. They're not variable speed pumps, or if they are variable speed, you want to start and stop them, or fixed speed pumps. You totally have that ability with the Viessmann control. We have this address 3A, and we have a control down by your pump module in all of these boilers, and these little DE contacts are programmed at these particular addresses. So 3A is programming the DE1 connection here. So when I close this contact, say with a zone in switch or a thermostat connection here, and I program this 3A from 0 to 1, when I hit this contact, what's going to happen is, and then when I program it, is the boiler is essentially going to kick that pump on for that system, and it's going to fire to that particular set point. So if I had one temperature, then I would have wire DE1 and adjust address 3A to 1. And now when I hit the contact, it's going to start and stop. They're going to start that pump. When I open the contact, it's going to stop the pump. If I've got a second temperature here, so HC2, I can take its end switches to the DE2 connection and go to 3B and adjust this to 3B to a value of 1. Thing for all the zones connected to that circuit, and turn that pump on and off, and mixing valve open and closed. And if I had a third temperature, HC3, I could take it to DE3 here and go to address 3C and do the exact same change. There's a couple of other addresses, basically for another time or a little bit, but just there's a couple other addresses to program all this stuff correctly, so that when we do hit that contact, the right things are going to happen. But effectively what you're dealing with here is, you can kind of think of these as the TT contacts for your different heating circuits. And the other advantage here is, if this high temperature circuit's not calling and one of the other lower temperature circuits are calling, it's going to basically, the burner is only going to, or the boiler is going to fire to the lower set point, not to the higher set point of HC1 here. So a couple of benefits of being able to do that with your system. When we are adjusting your heating curves for maybe only one circuit, or you might have up to 3 here, so it'd be 3 different circuits we're dealing with, there are 3 heating curve parameters that Viessmann controls give you. And this really allows you to customize your heating curves. And that's where the money is as far as energy savings, is to customize the heating curves. Lots of times we go to boilers and that this slope has never been changed from the default. Everybody's happy in the house, they're comfortable, but there really has been no adjustments made to that control. So there's money on the table. We understand that. The whole idea there is to dial things in to that particular home and the occupants of that particular home. Everybody's a little bit different. So we have a slope. So that's basically what we see here. That's what we pick when we are talking about design. You need a specific temperature going out to your heat emitter. When it's a specific temperature outside, that sets the heating curve. That sets your design conditions. So there's your slope. We also have a shift, and we have a room temperature set point that we dial into the control. So there's those 3 variables that we play around with when we start to engineer these systems, to really configure that for a really, customize it to that particular building or the occupants. So again, there's your slope. What we look at here, we've got the room temperature. You see, whatever the room temperature is here, that's where all the curves are going to go down to. So we've selected 20 degrees. You'll see all the curves go down to 20 on there, and we got a 1.4 heating curve, so with no shift. So basically, when the design temperature is at -20, we're going to be getting somewhere around 75 degrees C supply temperature going out to the building, about 167 or so Fahrenheit. When we're at 0 degrees C, we're going to be somewhere around 122 Fahrenheit, about 50 C. So that's where you can see how we're kind of changing the set point as the temperature outside changes. But there's also the shift. And in this case here, we basically took that same 1.4 heating curve and we put a shift in here of 10 Kelvin, or about 10 degrees Celsius. You can go between about -13 and about +40 degrees as far as Celsius or Kelvin in a shift that gives you this basically range or parameters. But you can see here, this was the previous with 0 degree or 0 degrees C or 0 Kelvin shift. There is the new temperatures with that 10 Kelvin shift. So you see that we had 20 degrees, now we're going out to 30, the same temperature outside. When it gets to 10 degrees, we were at 37, now we're at 47. So you see the trend basically is the shift just moves the curve up in that incremental value right across the curve. So now every temperature has been raised by 10 degrees when we use the shift. What I like to use the shift for here what I use it for is when I have a system set up, I got that 1.4 heating curve. The next year I go into that building and people are like, yeah, no, the system's been working great, no problems, comfortable, no issues whatsoever. I go in there and I'll take the shift and I'll drop it down. So I'll go from 0 down to -1. And then the next year down to -2. So as long as there's no problems, you just keep dropping that shift down, that drops the supply temperatures down. Remember your 3-to-1 rule. We're starting to get down to that sensible temperature, energy savings. The reality is people don't really care what the supply temperature is. They only care what the thermostat tells them, if they're comfortable or they're not comfortable. So the money really is in adjusting these heating curves to what we're looking for. That room temperature we're dealing with, how does the boiler know what the temperature is inside of the space? We do have indoor sensors that we can use called Vitrols. That's for another day. It is really a good, another component that we can use for energy savings, but we're really talking about basically trying to keep this to a limited time. The room temperature here is a nominal value. Think of it as you're telling the boiler, this is our goal. We're trying to reach 20 degrees C or 68 Fahrenheit in the building. So all the curves will basically go to that particular position. If I say 25 instead of 20, you see that the curves all pin now to the 25 degrees. The difference being now that at the original room temperature of 20 degrees C or 68 Fahrenheit, I was sending out 122 Fahrenheit water when 0 degrees outside. If I move that to 25, it gives me about a 62 degree Celsius set point now, about 12 degrees C higher than it was at the at basically 5 degree lower room temperature. So it's kind of like a shift, but much more dramatic depending on the heating curve that we're using or adjusting here. So the room temperature adjustment here basically gives you a little bit more of an unknown value of where that set point is going to be, but understand that as you increase that room temperature, you're telling the boiler, I need to send out a higher supply temperature to maintain that higher room temperature set point. And it also adjusts your warm weather shutdown point as well, right? So if I go from 20 to 25, my new warm weather shutdown point is going to hover around the 25 degree C mark. We're not back here in the 20 degree Celsius set point. So what's this do for us as far as power to make adjustments to the heating curve? Here's a nice example. You've got an issue where, during the shoulder seasons, there's not enough heat. The occupants are complaining, but during design temperature, when it's at the coldest temperatures outside, we're spot on, everybody's comfortable. So we understand that if we increase the shift on our curve, now we're going to achieve that bottom end shoulder season. We're going to increase the supply temperature going out, making the occupants more comfortable. But now we're overshooting. We're basically losing efficiency on the top end here when we're at design temperature. Well, if I boost up here and then turn the slope down, what I've done now is I've flattened my curve out. I've now customized my heating curve to the building. So now this is special. It's different from everybody else's heating curve, and it's now tuned into the people and the building that that particular unit is attached to. So that's what you have as far as a power here between those three variables: room, temperature, slope, and shift. You can really dial these heating curves into what you're looking for. And a couple other things that we have as far as heating curves go, you can also set minimum max. So you can put like a floor and a ceiling on your heating curve supply temperatures. So a fan coil, for instance, coming out of warm weather shutdown, or a piece of baseboard needs to have a fixed temperature to start out with, then we can basically set that at address C5 and say that when we start, it has to start at a specific point, and then that control will set that temperature until it gets to a point outside where it needs to increase. And then you see the blue is the reset point. but then we want to protect it from some other reason on this side where we don't want to go above 160 degree or 75 degree, 170 degree Fahrenheit. We put that ceiling on it here. So basically we have a starting point and an ending point and reset in between. And those are in your heating circuit areas, C5 and C6. Those are the default temperatures we see there, and you can put those caps on your system. We talked about heat losses of buildings. So shouldn't an outdoor reset control know what type of building it's installed in? So when you put a boiler in, and we don't tell the boiler this is a really high efficient energy saving home, it's got R50 in the walls, or this building was built back in the early 1800s, it's got seaweed in the walls for insulation, it's got single pane drafty windows, those types of things. So each one of those buildings is losing heat at a very different rate, and we have to tell that control what that rate might possibly be. And with the Viessmann control, we have this time constant, address 90, which is it's basically in a really safe position at 36 value here, where it basically adjusts it gives us an average or a time constant here. So it takes a 6-hour period and it averages out the outdoor temperature over a 6-hour period. And what it's trying to do is trying to dampen out, and that's what they call it, a damped temperature here. So you see this in on our controls. What's that damped temperature? That's this address 90, averaging out the outdoor temperature over a period of time. So the advantage of this is if I have a really well-insulated building, and that building we don't have to react to the outdoor temperature changes as quickly as a poorly insulated building, I can take address 90 and stretch that averaging out over a longer period of time, which means that as the temperature outside is changing, the boiler is not really adjusting as quickly to those outdoor changes. So sort of flattening it out, making it more gradual so that the burner isn't basically trying to hunt for different set points, increasing and decreasing. It just basically makes everything much more smoother in operation. So that's the important thing here. Our control will tell you where, basically give you some level of ability here to input what type of building we are basically installing that boiler in and allow that control to compensate for it in there. So this is how that damp temperature is actually used for your control. When the control is using an outdoor temperature, for your reset curve, it takes the actual temperature, adds that damped outdoor temperature, divides it by 2. That's the average temperature that we use. So in this case, at 11 degree damped and actual at 10, we were at a 10.5 degree C temperature outside. So it makes basically a compensation there to give us a much, basically a much smoother reaction of our heating system. So if there's some issue there, obviously it's in a safe point at 6 hours, but you have the ability and power and authority there to make those changes and adjustments to tweak it for your particular system. Some other things we have too, outdoor, warm weather shutdown. We call it heating circuit pump logic function. Essentially, we turn the pump off when the temperature outside gets to a specific point. We don't heat that particular space anymore. This address A5 is set to 5. So essentially, we have 20 degrees C inside a little building here. That's that room temperature set point, the nominal value. If the temperature outside here gets to 21 degrees, so 1 degree above the room temperature set point, we're going to go into a warm weather shutdown point at that level. And that's adjustable. You can do it, from within the parameters here from 1 to 15, you can make an adjustment here to when that particular warm weather shutdown point or heating circuit pump logic function is going to happen with that. And we also have timers, and a lot of people are looking at the timers. What we're doing here as far as efficiency changes, we are reducing and changing the actual temperature of the water, not the temperature of the air so much. So as far as our efficiency goes, much more efficient if we are reducing the supply water temperature going out to the building than basically just putting a reduction on our thermostats, allowing the boiler to fire at that exact same temperature. It kind of essentially does the opposite as far as efficiency goes. It actually starts to short cycle the system a little bit when we do that. So this is reduction in supply temperature based on a time program you can put in there. So just like your programmable thermostats, we put in a time when we want heat to be at a specific level, and in between those periods, you see the darkened areas here are times when the system is in the off position or reduced mode and sending out a lower supply temperature. So how that works is during the normal operation, we have the sun area here, or the sun represents the normal operation, and the little crescent moon represents when we go into night setback. So from 10 at night till 6 in the morning, we go for basically, we reduce from 20 degrees down to 14. So pretty dramatic change here, but just to kind of give you an idea what happens. And you notice that when we hit that 10 o'clock, all those curves now shift down to the 14 degree room temperature set point. So if the temperature outside is above 14, we go into warm weather shutdown. Basically, the system shuts off. We don't supply any heat. If there is still a call for heat there, the temperature is still cold enough outside, like 0 degrees, for instance, then we would go from a 50-degree supply temperature down to 37-degree C supply temperature going out to the building. So a drastic change here. Remember 3 to 1, remember condensing. All those things are starting to come into play here to increase the efficiency of the boiler by using this. So people would, look at that and say, well, it's not going to be very effective as we talk about changing in temperature here for, high mass systems. But really, high mass, again, is that low-hanging fruit. Probably don't want to do a lot of temperature adjustments to high mass systems because of the, flywheel effect, and, you might need some different types of sensors to really pick that up accurately. But for baseboard systems and fan coils, this is very realistic to type of capability to be able to do, where you can start to play around with those timer programs. And there is already logic in the control that will compensate where we say, well, if that temperature gets too cold outside at night and we're in night setback, we're going to have a problem picking the system back up again in the morning when we come out. There's a built-in logic that's already defaulted in the heating circuit programming and coding, F8 and F9. Basically what this is, if you look at it, as long as the temperature outside stays above -5, you'll stay in night setback. But as the temperature outside starts to drop and we hit about that -5 degree point, what's going to happen after -5 and we get colder outside is the control is slowly going to take us out of the night setback. And eventually it's going to get us into normal operation again. So at about -14, coded in F9, once we reach that outside, the boiler is now just a normal operation again. So essentially, so that we don't get to that, time in the morning we want to get the temperature back up, where we have a large pickup that's going to be problematic. So this is by default going to basically adjust the temperature, supply temperature, as we start getting into some extremely cold times of the year. So this is programmable for you. By default, it's there. We also have a boost function capability built in the control. So without using the function in the previous slide, what we can do is a boost factor. So we can say, when we get out of night setback and we get to 6 o'clock in the morning here, and we're trying to get the temperature up in the building, you have the ability of raising the percentage of that supply temperature. So if the temperature was going out at 122 degrees Fahrenheit, we can say, well, we want to boost that by 20%. So for now, what we're going to do is boost it to 60 C or 140 Fahrenheit for a period of time to help quickly raise that temperature to get this up to our desirable temperature a bit quicker. And then FB is a limitation on how long this is going to be able to do that. So by default at 60 minutes. For an hour, it will allow us to boost that temperature by 20%. After that point, it's going to go back to normal operation here. So I kind of get that idea there that these are all built in. It's just about, do you want to use them or not? They're available to you for all 3 of your heating circuits that we are utilizing. Of course, we have holiday programming. So we go back to those, the family sitting on the sofa talking about their trip to Disneyland. Well, it's finally that day when they're going to leave, go to Disneyland. They could program in here on their 200, 300 level controls when they're leaving, when they're returning. That system's going to go back into nights. It's going to basically go into a sleep state while they're away, not heat the domestic hot water tanks, saving them energy. When they come back this day, on the 12th, the 22nd of December here, at midnight, that system's going to go back into normal operation. The tank will be hot, the building will be warm, as if they never left. So again, it's about energy savings. This stuff is available in the control that you know it's there and that you can utilize it. So finally, just working through basically the different boilers we're talking about. So we talked about 300 level and 200 level controls. We have 200 level and 300 level boilers here. The CU3A is the 300 series. It's a high mass boiler. The B2 series boiler here is the Vitodense 200, has a 200 level size boiler. So the 200s are the wall mounts, the 300s are the high mass floor mount boilers. And we see here a difference. The same inputs, 199,000 BTUs, but this boiler is over 100 pounds heavier, 140 some pounds heavier, and it has about 4 times the amount of 4 or 5 times the amount of water content in it as well. So it's got much more mass to it, and we can basically use that mass to our advantage, depending on our operation here. So going back to a little bit of literature here, we've all gone back and read a little bit of Shakespeare, and we had the old quote, "To be or not to be, that is the question." Let's put that into the hydronic context here. To pipe or not to pipe? That is the question. So are we going to use primary, secondary, this closely spaced tees? Is it useful? It just depends on what we have for a system here. So we have to consider the type of boiler that we're applying and whether or not this is going to be an advantage or a disadvantage to us to decouple the boiler from the actual heating system itself. So a couple of factors to look at here. One is pressure drop of the heat exchanger. That's specific to the type of boilers that you're kind of using out there. So our water tube heat exchanger, if you were to put a couple pressure gauges across here, the maximum flow rate in the 68 to 125,000 BTU Vitodense 200s is about 6.2 gallons a minute. And at that maximum flow rate, your pressure drop would be about a little over 18 feet of head. So it chews up a lot of the head capacity of your pumps. Larger boilers, the 399 to 530, they're at about a 38 gallon a minute maximum. So right around a little over 15 and a half feet ahead of basically pressure drop, just pumping the water through the heat exchanger and back out again. So not accounting for the system that you attach that to. So basically you're kind of looking at, how big does that pump have to be to use one pump to basically feed the system as well as that boiler. So one consideration there. If we compare that to a CU3A boiler, so we look at the heat exchanger here, doing the same thing, P1 and P2 here, put our pumps on. Down here, we have a graph, or basically a list saying if we wanted a 20-degree delta T, depending on the type of boiler we're looking for here, 94,000 BTUs at a 20-degree delta T, or 199,000 BTUs at a 20-degree delta T, there's the pump's capacity, the flow rates we're going to need. So a 20-degree delta T, to get 94,000 BTUs, we need 9.9 gallons a minute. So about 9.9, we're going to be a pressure drop of about 9 inches. So not even a foot of head pressure drop that we'll be dealing with here in the CU3A94. If we were dealing with the 13.3, the 125, 13.3 gallons a minute, we're at a little over a foot of pressure drop, 16.14 inches. We have 17 gallons a minute here at about 11 inches on the bigger boiler, so that's the 160. And maximum 22, a little over 22 gallons a minute, we're at about just under 20 inches of pressure drop for the bigger boiler. So basically negligible pressure drop, so not using a lot of that pump head to push the water through the boiler. So advantage high mass here is that we don't have to worry about that pressure drop through the boiler. The other thing we want to think about is more between the masses of the boilers, not so much about the configuration of the heat exchanger, but to what amount of mass and turn down do we have in the boilers, and how many zones, and how much we've microloaded that system. So what we're talking about here basically is we sized the boiler for the heat loss of a building here, and then we took that building's heat loss and we chopped it up in a bunch of little zones. We put a big, put a bunch of masters in there with the thermometer, with the thermostats, of course, controlling the zone valves and opening and closing those. So it all comes down to basically we size the boiler and the pump here for when all zones open. So when one zone's open, of course, the boiler sees that, remember that's section number 3, as a difference in load here. So as the zones open up here and more flow rate goes to the boiler, the burner is going to operate and modulate up to basically increase the BTU input because it sees that we're falling off of temperature. It wants to ramp that up and get it up. A third zone opens, the burner ramps up more. You're at design now, all four of your zones are open, maximum output, burner's firing up, and then zones start to shut down. And of course, as those shut down, it's very difficult for us to know the flow rate other than at design temperature, or design criteria here. And when you have a low mass boiler and you have that boiler firing, every time you have it firing, there's already a set point that it has in mind. It's already there. And as we open and close those zone valves, the burner, if it's basically up close to that set point and a zone valve closes, it may not have enough capability to ramp that down fast enough before it hits set point and then cycles off. So as those burners cycle off and they come right back on again, you're dropping your efficiency of your system. Even with high turndowns, it's possible where we're not going to match that drop and flow rate enough where that burner is going to stay running. It may basically delay enough where that shuts off and it has to come right back on again. And that's going to lead to more wear and tear on the boiler, higher fuel bills, your combustion efficiency drops. All those things are not good as far as your efficiency of your burner. And that's where the primary secondary piping comes into play. So when we start dealing with boilers that really work better with constant flow versus a varying of flow rate as the zones are coupled directly to the boiler, we want to separate those two. So we add another pump for the boiler side. We got the system pump over here looking after all the flow rates through the system. And if we look at this, the whole goal with basically this hydraulic separation or primary secondary piping is when we have flow in one side of the system, you'll see there's no flow in the other side. So we have a piece of piping right here we call the common piping. It's common to both the primary loop and the secondary loop. If you put pressure gauges here and we were monitoring the pressure drop between these 2 points when we had flow, we want to see basically zero difference between those two pressure gauges. So when there's zero difference, the water doesn't see a pressure differential and it doesn't know that this side of the piping is available. It just cycles right through there on the common piping. Same if the secondary pump is running by itself with the primary off. If there's no pressure differential between the common piping here, then there is going to be no flow of water moving back up into the boiler loop. So it basically cycles around here. So your goal for primary secondary is to have a zero pressure drop between the closely spaced T's here, and that's going to be effective as long as there's other rules here as well that we got to look at, but primarily that is what the magic behind primary secondary is, to ensure that when pumps are flowing and other pumps are off, we're not moving flow into those particular areas of the system. And the other advantages to low loss headers, obviously they provide air separation. I know in some areas, local authorities having jurisdiction in our area here in the lower mainland of BC, if you put a low loss header in or a hydraulic separator or a primary secondary header, whatever you want to call them, they see those as equal to air separation as well. So they'll essentially, if they see the low loss header in place, you won't have to add an air separating device onto that system. So you can take that money, put it into something that adds a bit more value here, where it does both air separation. It also adds some mass, so we add more water here. Every bit more mass in a low mass system is going to be beneficial to keeping that burner running. And also you can get some dirt separation. And some manufacture these, they'll add magnets, et cetera, to them to really basically add that dirt separation there. We don't do that on ours. The reality is there's lots of different types out there as far as primary, secondary headers or low loss headers. The key there is that they add a lot of extra value when you purchase those, and each one of them have their own application. You might need a copper primary secondary header versus a cast one, for instance. So different things require different types of situations. So we're just here to basically promote efficient operation systems. So whether you use a Viessmann low loss header or some other manufacturers, it's basically how it adds some extra value to your system. It also could be detrimental depending on the application. So we don't always want to use primary, secondary, and condensing boilers, high mass being one of those applications, because it's not really impacted by changing of flow rates through the boiler, et cetera, because of that mass of the system. And this is kind of trying to explain why that might be undesirable. So if we have basically a primary secondary system, so whether it's closely spaced tees or a low loss header here, we have three particular types of situations that could occur. If the flow rate on both sides, the boiler side and the system side, are the same, it's just a piece of common piping, just a conduit where basically the flow rates are the same. So basically the temperature on this side is going to be the same as the temperature on the supply side. Same with the return temperatures going back and forth here. If you have more flow rate on the boiler side of your system, what's going to happen is we're going to be bypassing some of that boiler supply water back to the return, elevating the return temperature. So we have a system here where we have more pumping on the boiler side versus system side. We're going to bypass some of that flow. We're going to see why that happens here in a minute. Or alternatively, you could have a flow rate that's lower on the boiler side than the system side, and now we're mixing some return water back up, and now we're going to have a different temperature going out to our heating system. So how does a boiler know it's piped primary, secondary? It's a pretty important thing for a boiler to understand, because it could be in one of these three different scenarios, and we want the boiler to be able to understand where it's at and react to it without basically overshooting or undershooting temperatures. Again, basically increasing the cost and maybe reducing the comfort level of the building. So let's check a typical system here. And you can basically, if you know the different variables here, we can just work out different temperatures. So if we wanted a situation here where we had more flow on the secondary side than the primary side, you see we have 6 gallons a minute on the primary side. We got 10 gallons a minute on the secondary side. We got a bunch of zones open here. We can't have more flow on the return than on the supply. So if I've got 6 gallons a minute going in, I got to have 6 gallons a minute coming out. If I got 10 gallons a minute coming in here, I need to have 10 gallons a minute coming out on this side. So what happens to that extra 4 gallons a minute that comes into our low loss header is that 4 gallons bypasses, mixes with the 6 gallons from the boiler to give us our 10 gallons out. But we're mixing 90-degree Fahrenheit water with 130. That means that this temperature is not going to be 130 here. So if we look at the equation here, what we end up with when we do the math on it is that the temperature here is about 114 degrees Fahrenheit. So unless your boiler knows that there's an issue here, the only possible thing you could do is overshoot the boiler set point so that we know that we can make the temperature over here regardless of what the flow rates are going on. So we need to be able to adjust the boiler temperature here to compensate for this reduction in supply water temperature. In the Viessmann world, we use what we call a low loss header sensor. Really, it's just a secondary supply temperature sensor. So if you're using closely spaced tees, or you have another primary secondary header that's not a Viessmann, you can add this sensor to the boiler. It comes with every single one of these boilers, whether it's a Viessmann 200, a 399, or the 68,000 BTU boiler. They all have outdoor sensors. They all have these low loss header sensors, secondary supply sensors. We now install that to pick up this supply temperature. And now, because it has this, it knows that it's part of a primary secondary system, and this could happen where we've got more flow rate on the secondary side. So what happens now is there is a new calculation that is utilized by the boiler control. So with the supply sensor here, the boiler temperature set point is now going to be a function of the desired supply temperature. So what we're looking for to go out here, added to that, the desired supply temperature minus the actual temperature sensing picked up by the low loss header sensor here. So in our example, it would look at if we had 130 degree on the desired supply temperature here, we add to that 130 as our desired supply temperature minus the actual temperature. So we add that 16 degrees to that boiler set point. The burner or boiler is going to fire to 146 Fahrenheit to basically make sure we get 130 Fahrenheit going out to our system. So without some sort of feedback going back to your boiler control, the only way that boiler can maintain the loop that we're looking for here is to really overshoot on the primary to make sure that we get that, because it has no clue what's going on here. You need some sort of feedback temperature here to make sure that boiler control can reach that temperature effectively. So not overshooting, but supplying exactly what we're looking for. And the same on the reverse here. If we are looking at this where we have a reduction, now we have more flow rate on the primary side versus the secondary side. That boiler sensor coupled with the supply sensor going out here will anticipate when they start basically getting to the same temperature, that burner knows to stay in low fire. So the whole idea here is just like we looked at the number 3 sensor previously, it's going to avoid cycling the burner as much as possible by reducing the modulation of the burner. So both of those temperatures feed back telling it, yeah, you're already at, we're basically well within range here. Keep that burner at low fire to stop that cycling of that particular burner. So all these things go towards helping that unit basically stay in good functioning operation. All right. Finally, so we're coming at the end of the road. Thank you all for staying with me. Final thing is look at the top picture here and the bottom picture. Which boiler do you think is going to be more efficient in operation? I'd say the top one as well. I know you all said that. The bottom boiler, if we're dealing with fossil fuels, look at the different molecular structures here that we have for natural gas and propane. The carbon, any type of unit that's burning a fossil fuel, you're going to have hydrocarbon deposits. You're going to have deposits of basically the debris that is part of that molecular structure. It's going to fall out and dissipate. We have to be able to clean these. So as we cover heat exchanger, and that's what soot does and debris, it basically reduces the heat transfer between the water going through the coil and of course the flue gas is moving through the burner. So as we pile up this debris, we reduce the efficiency of the boiler, which adds more cost to the heating system year over year. So maintenance is a primary thing. We put this investment into these high-end products, and now as if I have any homeowners that are tuned into this, how important it is for you to service your boilers as they're in operation here. That's going to give you basically money back as far as operation, because you're going to have less wear and tear in your boiler, less issues as far as lockouts and all those types of things, as well as if your boiler is maintained annually, your heat transfer virtually doesn't change all that much year over year, and you have essentially that boiler at its peak efficiency continuously versus basically starting to struggle as we accumulate soot and debris. So the benefit of a Viessmann 200 boiler is it's low mass. Those coils are very tight here, but when you take that burner off, you got full disclosure of what needs to be cleaned. It's right there in front of you. You can see it, and it's accessible for you to do that maintenance. On the higher mass boilers, this is a CU3, again, a little less of an issue because of the larger flue gas passageways, but again, we're dealing with fossil fuels here, carbon. We're going to have to clean those surfaces to maintain those units as well. So we actually have a final slide here. Basically, we have an address here. I think of it kind of like some of those thermostats out there where they have a change your air filter type of alarm that comes up on the thermostat face to tell the homeowner to go down and turn that, change that air filter in their furnace. We have these addresses here, and basically you can program in a time. So whether it's run hours or amount of months. So address 21 would be an amount of hours of runtime on the burner. 23 would be instead looking at months of operation. And basically what's going to happen is you set that, and it's going to start from the time you set it. And if I set address 23 to 12, for instance, after a year of operation, the boiler is actually going to alarm. It's going to basically send out a fault flash on the control screen. A little red light's going to flash. The burner is still going to fire. Like nothing is going to change as far as the operation of the burner, but what it's trying to do is give the occupants a heads up that there's something going on here, and that will essentially give them some sort of indication it's time to service the boiler. So we do have this ability on the controls to even program when it's time to service the boiler. That way there we maintain or give a good reminder to people that it's time to call the service tech to go in there and basically do that service to keep that burner in efficient operation. And then when you go in there as a burner tech, you'll just go to address 24 and reset it from 1 back to 0, and that will reset the time clock here for another 12 months of operation. All right, so that's it. Thank you so much for hanging with me there. As we say, this was the first presentation of this particular online forum. And we are, like I say, we call this the dress rehearsal. So we're going to do this again next week, and we'll probably tune it up a little bit. But I hope you guys got a little bit of, some nuggets out of information that we presented here, and just really appreciate you kind of hanging, because I know I went a little bit longer than I should have. But thank you so much. And any questions out there, Mark?
We got them all answered. There was
Nice.
as you were talking about a topic, you answered it before I could type it in fast enough. So you actually answered it. I answered it anyways, but you answered it.
Yeah, that's the thank you for coffee, right?
Yeah, that's right.
Yeah.
I like the way you explained a few of those things. I'm going to reword the way I talk about stuff to incorporate the way you said it. So I'm going to have to go back and listen to the video so I make sure I get the verbiage right, because I think your explanation of the heat transfer across the heat exchange in the closest space T's was really, really well done. I think it helped a lot of guys understand that.
I hope so. That's what it's all about. I mean, we've done this. I know Jody Samuel has done some excellent presentations down in the U.S. as well. Guys are probably tuning in and talking about condensing. Mark did one just a couple weeks ago, same kind of idea, but just present a different way. And like I say, it's all about repeat, and get that information out there in different formats, and hopefully people will lock on that stuff and get a better grasping of it. And like I say, we learn it every day. Everything's something a little bit different that we learn every day. So it's just about getting that information out there.
And everybody that was here today will get a copy of the PDF of this presentation and the questions and answers that I typed in. The video will be posted online to our YouTube channel. It usually takes me a few days to patch it together and make it pretty, but we'll get it up really as soon as I can do it.
Excellent. Well, if there's no other questions, I guess we'll see maybe some of you might tune in again next week. But if you had some people that didn't have a chance to come into this presentation this week, we're doing it again next Thursday, I think, Mark, if I'm not mistaken.
Yeah, same day next week.
Okay, and we'd love to have them here. So until next time, thank you, folks, and have a great day.